Second talk is CIPHERMATCH. That's from Mayank and from ETH3 under the advice of Professor Onur Mutlu. And let's see if it's ready or not. I think this is yet another fairly kind of hard problem because the matching itself is fairly expensive and homomorphic encryption. So let's see how the team solve the issue. Okay. Let's welcome. Sure.
Thank you, everyone. Hello, I'm Mayank Kabra, and today I will be presenting our work, CIPHERMATCH, accelerating homomorphic encryption-based string matching via memory-efficient data packing and in flash processing. So let's briefly go into the executive summary. So secure string, exact string matching using homomorphic encryption face performance bottleneck in two key areas. First is the use of complex homomorphic multiplication, and second is the data movement bottleneck because these large encrypted databases are stored in the SSDs. Our goal is to develop an algorithm hardware co-design to provide scalable, parallelizable, and efficient HE-based secure exact string matching. And our key idea is to use only homomorphic addition operation and perform in-flash processing by exploiting the operational principles of NAND flash memory to accelerate the secure exact string matching. To this end, we propose CIPHERMATCH and a new algorithm hardware co-design that significantly improves the performance of HE-based secure exact string matching by using only homomorphic addition operation, by optimizing the data packing scheme, and by designing a new in-flash processing architecture. We observe that our CIPHERMATCH algorithm provides 42.9 times speed up and 39.4 times energy savings over the prior state of the art in software, and CIPHERMATCH when integrated with in-flash processing further provides 136.9 times speed up and 256.4 times energy savings over CIPHERMATCH software implementation. This is my talk outline, and first we will briefly go into the background, key problem, and our goal. So exact string matching is used in many security critical applications such as databases, for example, searching a query in sensitive database, or bioinformatics, for example, identifying similarities in DNA sequences. Now let's look at a very simple example. Assume a user has a query, and in the server we have the database which is stored in the SSD. The user will send the query to the server and will perform the string matches, and whenever the match is found, the result is sent back to the user. However, performing computations on plain text can lead to data leakage, where attacker can see the computations being performed and can retrieve back the data. Now, homomorphic encryption can be leveraged to perform secure exact string matching. Now, let's see how secure exact string matching is performed. So user will encrypt the query and send this encrypted query to the server where the encrypted database is stored. Now user will perform homomorphic operations where he is allowed to compute on encrypted data without decrypting it. And finally, the encrypted result is sent back where the user will decrypt the result and get back the final match index or whatever he wants to. Now there are secure string matching using HE can be performed using two key approaches. First is by Boolean approach and second is by arithmetic approach. In Boolean approach, we encrypt individual bits and use homomorphic XOR and AND operation. And in arithmetic approach, we encrypt multiple bits, packed bits, and use homomorphic multiplication and addition operations. Now, we observe some common characteristics such that Boolean approach have very high memory footprint and high computation cost because we have to perform operations on individual bits. Whereas in arithmetic approach, we observe a lower memory footprint and lower computation cost because we are packing multiple bits together. However, there is a trade-off that Boolean approaches supports flexible query sizes, whereas arithmetic approach does not support, they only support limited query sizes, which is because we have to perform homomorphic multiplication operation, which increases the noise. Now, we have more detailed analysis in the paper. However, there are prior approaches like in both arithmetic and Boolean approaches, and we will focus more in the slides for the arithmetic approach. Now, let's look into more details how arithmetic approaches are used. Assume a database. Now, first we will take multiple bits of the database and place them into the elements of the plain text vector. Now, we will encrypt it to generate the ciphertext. Now, we will take the individual bits of the database and place it into the elements of the plain text vector. So each element will have one bit, where the encrypted database will have, let's say, for example, 32 bits. And then the elements is in the plain text vector will be 1024 elements, whereas after encryption, it is 2048 elements. Now, if a conventional database size is 128 bytes, the encrypted database size is 8 kilobytes, which is an increase in 64 times. The second step is to perform homomorphic multiplication and addition operation in these arithmetic approaches. For example, assume this as an encrypted database. We have an encrypted query. We'll perform homomorphic operations, a sequence of multiplication and addition operations to generate the final encrypted results. With this, we analyze one of the prior approach, arithmetic approach, which is best in terms of performance, in terms of execution, total execution time. And we observe that 98% of the total time is spent on homomorphic multiplication operations. And this is because homomorphic multiplication is 100 times slower than homomorphic addition operations on a conventional CPU system. And this brings us to our key problem 1, that homomorphic multiplication limits the scalability of this HE-based string matching algorithm. Now, databases are large and they are stored in SSDs. Homomorphic encryption will further increase these database sizes. Now, this brings us to our second key problem, the data movement bottleneck. Because we need to read these databases from the SSD, the external I/O bandwidth of the SSD is the main bottleneck for reading these encrypted large databases and perform the computation. However, prior works have shown that we can reduce this data movement. Now, these encrypted databases are usually stored in the flash chips, and prior works have shown that we can use in-flash processing, which enables computations inside SSDs by exploiting the operational principles of NAND flash memory. With this, our goal is to develop an in-flash processing-based algorithm hardware co-design system that can perform scalable, parallelizable, and efficient, secure exact string matching. Let's move into our key idea. So it comes from a key observation. Assume a database and a query. If we negate our query and send it and perform homomorphic addition, performs conventional addition operation. Once the query matches, we will observe a string of ones. Now it means that in a conventional database, we can perform only addition operation to get a string match. This means that this observation can be extended to secure exact string matching, where we can use only homomorphic addition operation to perform secure exact string matching. Now let's look at how this encrypted database, and we will perform it in the encrypted domain. Now assume a same query, we negate it, we encrypt it. Once we send it to the database, we perform homomorphic addition operation. And if a encrypted query matches, we will get encrypted value of 111s. Now this can be matched, and then we will see later how we will perform, how our algorithm performs this. But this brings us to our first key idea, that we can use only homomorphic addition to perform secure exact string matching. We also observe that homomorphic addition is highly parallelizable, and we can exploit the inherent parallelism of NAND flash memory, which improves the performance and which reduces the data movement. Which brings us to a second key idea, that we can use in-flash processing to reduce data movement and accelerate secure exact string matching. With this, we propose CIPHERMATCH, an algorithm hardware co-design that improves the performance of HE-based secure exact string matching. CIPHERMATCH reduces the memory footprint by optimizing the data packing scheme, eliminates the costly homomorphic multiplication by using only homomorphic addition operation to perform exact string matching, and reduces the data movement and leverage the inherent massive bitwise and bit level and array level parallelism by designing an efficient in-flash processing architecture. Let's move into CIPHERMATCH system overview. How CIPHERMATCH looks like. Assume a client and a server, and then we have client has a database, and client will efficiently pack this database to reduce the memory footprint after encryption, and will store it into the server's SSDs. Second, client has a query and wants to perform string matches. Client will efficiently pack this query and perform parallel secure string matching on this encrypted database. Third, the database is loaded from the SSDs, the encrypted database is loaded, and we perform only homomorphic addition operations to perform secure exact string matching and send back the result. And to accelerate this overall process, we exploit the operational principles of NAND flash memory to accelerate a secure exact string matching. Now, CIPHERMATCH involves 3 key steps. First is a memory efficient data packing scheme. Second, secure exact string matching algorithm. And third, in-flash processing. Now let's move into CIPHERMATCH algorithm, which consists of the first 2 key steps. Let's look at them one by one, which first is the memory efficient data packing scheme, where we efficiently pack the query and database to reduce the memory footprint and enable parallel string matching. Now assume a conventional database and a conventional query, and let's look at how we'll encrypt it. Now with this database, we take multiple bits and then place them into the elements of the plain text vector and then encrypt it to generate our encrypted database. So essentially, we have encoded the database by packing multiple bits into the plain text vector. For example, we will take 16 bits and place it into the plain text vector, and once we encrypt it, it will be 32 bits. And then we have 1024 elements in plain text. After encryption, the ciphertext contains 2048 elements, which means we observe that the increase in encrypted database size is only 4 times. Now for query, we will first negate the query. We will replicate the query in the elements of the plain text vector, and then we will encrypt it to generate the encrypted query, and we replicate this query so that we can perform parallel string matches that we will look in the later slides. So we have encoded the query by negating and replicating it into a single plain text vector. Now with this encrypted database and encrypted query, let's look at how we'll perform secure exact string matching using only homomorphic addition operation. Now, essentially we want to perform a homomorphic addition, and homomorphic addition is inherently an element-wise addition of these elements. So we perform an addition operation, we get the final result. If we decrypt the result, we will observe that in one of the elements, we will find a string of ones, and it means the match is found. However, we want to find the match on the encrypted result because the server will contain the encrypted results. Hence, we generate a match value, which is basically a string of, in each element, we will contain a string of all ones. And once we encrypt it, it will generate an encrypted match value. We'll compare the encrypted result and encrypted match value, and we will generate the index and send this final index back to the client so that we can get the location, whether the index has matched, whether the query has matched or not. Now to summarize, we efficiently pack the encrypted database using our memory efficient data packing scheme. We negate and replicate the query so that we can perform parallel string matches, and we send it with an encrypted match value. And then we perform string matching using only homomorphic addition operation. Now let's move into our CIPHERMATCH hardware design. Now, what we want to do is to perform secure exact string matching inside SSD using in-flash processing. Now let's look into more details of how an SSD looks like. SSD contains an SSD controller, and it is connected with the NAND flash chip so that we can communicate with them, and contains an internal DRAM so that we can buffer the intermediate data. Now each flash chips contains multiple dies, and in each dies we have NAND flash cells where we can store our data. And in this NAND flash memory, we have a latching circuitry which consists of multiple data latches and sensing latch. Now prior works has shown that we can use this latching circuitry to perform computations, but they are restricted to only performing bitwise operations. There are advantages of performing this secure string matching in SSD. As we saw, homomorphic addition can be parallelized, and we can exploit the bit level and array level parallelism of NAND flash memory. Let's look into more details of the storage, how the storage system looks like. We want to perform homomorphic addition inside NAND flash memory where the encrypted data is stored, and we want to generate the final index that we saw in our algorithm by comparing it with the match value. Now for the first, we want to perform element-wise addition inside NAND flash memory. And with this, let's look at our third key step, which is to exploit the operational principle of NAND flash memory. Now, in this NAND flash memory, where the data is stored, we use bit serial addition to avoid carry propagation across different bit lines. Now, let's look into more details of this NAND flash memory. Assume the encrypted database that we had. In each element, we have multiple bits. So we will lay out the data vertically in the NAND flash memory. And in each bit line, we will perform the computations, and this will be across all multiple bit lines. Just to remind back, we have a latching circuitry which consists of multiple data latches and sensing latch which can store the intermediary data. Now, first step is to send a query from the SSD controller to these latches. Then perform a sequence of steps which will generate the sum bit and carry bit. However, we don't have enough time to go through the details of it, but you can check out more details of individual step in our full paper. Finally, we accumulate the sum bit and send this accumulated bit back to the SSD controller where the final match can. We have performed homomorphic addition. We want to generate it with the match value, and we do it in the general purpose core of the SSD controllers, so which is done in a pipeline. Software-based CIPHERMATCH by modifying the Microsoft C library, and we evaluate it on various query sizes and various encrypted database sizes, where we used all circularly shifted queries so that we can find different variants of the query. Now, for speed up for different query sizes, the Boolean approach is set at y = 1, and we make 3 key observations. First, arithmetic technique outperforms Boolean technique by order of magnitude because we have efficiently packed the data, and then we are performing on very less memory footprint. Second, CIPHERMATCH software, our implementation outperforms best prior arithmetic technique by 42.9 times. Third, CIPHERMATCH speedup increases with query sizes because we have eliminated the use of homomorphic multiplication. We are only using homomorphic addition operation. Now we evaluate in-flash processing based CIPHERMATCH implementation also by modeling the characteristics of NAND flash memory. And we evaluated against 3 baselines. First, CIPHERMATCH running on a compute-centric system. Second, on a memory-centric system. Third, on a storage-centric system. And again, we evaluate for various query sizes and various encrypted database sizes. Let's again look at speed up for different query sizes where CIPHERMATCH software is set at y equal to 1. We make 3 key observations again. All 3 near data processing system improves performance by reducing data movement. CIPHERMATCH in flash processing outperforms CIPHERMATCH software by 136.9 times. And CIPHERMATCH in flash processing outperform all other near data processing systems also on average. We also observe that CIPHERMATCH in flash processing speed up decreases with query sizes. This is because we have to perform repeated flash operation on this same data for circularly shifted queries. We also have energy consumption result where all 3 near data processing system provide large energy saving, and CIPHERMATCH in flash processing provides significant energy savings over CIPHERMATCH software by largely reducing data movement. We also provide more detailed observation from our evaluation section, an end-to-end system design, how operations are performed in vertical layout, and how can we enable CIPHERMATCH in commodity SSDs, an overhead analysis of CIPHERMATCH hardware, and how we perform bitwise operation using a NAND flash memory. And for this, I invite you to check out our full paper. To summarize, we propose CIPHERMATCH, a new algorithm hardware co-design that significantly improves the performance of secure exact string matching algorithm. We have 2 key ideas. First, to pack multiple bits of database and eliminate homomorphic multiplication, which reduces memory footprint and provides scalable secure exact string matching. Second, to use in-flash processing to accelerate. Second, to use in-flash processing, and which reduces data movement and leverages bit level and array level parallelism. And we observe that both CIPHERMATCH software and hardware provide significant improvements over state of the art. With this, I finish my talk, and I will be happy to take the questions.
Any questions? Okay, go on. Mike is coming.
Hey, this is Brandon Regan with Memory. Awesome talk, great work.
Thank you.
I'm just curious because the CIPHERMATCH and FHE are not going to be sensitive to any faults. So you're doing your compute in the bit lines and the bit cells. Is there any concern about reliability of those computations, or how's the fault rate compared to like CMOS?
So essentially what we have used is a prior technique, which is Flash Cosmos, which is already published in prior conferences. So what they do, as you said rightly, that NAND flash memory has fault. There's current state of the art NAND flash memory has some faults over some sort of program and erase operation. But the prior works have shown that we can use an enhanced SLC mode programming so that we can separate out, so we can reduce the errors or eliminate those errors. So based on those prior works, we assume that we will be performing in the SLC mode of the NAND flash memory, and that means that we are error prone by using those techniques. Yes.
Okay. Any other questions? So, oh, sorry.
I cannot hear you. Can you
Pick up?
Hi, this is Yash. I'm from university. My question is like, how do you can you elaborate on comparison on screen matching on the server?
So you mean how did we do that? So basically, once we have, so what we show that is that we have to perform and we have to gather the match on the encrypted result. Like if I can go back to the slide, let me just quickly do that. So essentially here. So what we show is that when we perform homomorphic addition operation, we will get these final, once we decrypt it, we will get that, okay, one of the elements has a string of ones. Now we cannot decrypt the results on the server. So how we should find the match? So we will create a match value in which all the elements of the plain text will contain a string of ones. Now once you encrypt it, it will generate an encrypted match value. Now this encrypted match value and this encrypted result are matched, and then you will find that both of the elements in this ciphertext are same. This is based on the fact that the errors, the noise, the errors that we embed into the original database and the query, those are, let's say, error 1 and error 2. The encrypted match value will be generated from these error 1 and error 2. And that's why we will find that the string of ones are actually correct. are actually the same. And that's how we find the match. Thank you.
Okay, sorry, wait for the mic, name and affiliation. You're famous, but.
My name is Anjun Kim at Yale University. So in that case, the client and server has the same key or different?
So initially, how the system looks like is that, let's say I assume a one such scenario where I have my own database. I will encrypt the database and store it to the server. Now I have the query that I want to perform a match on this. Now I will perform an encryption of that query, and that now I know the error 1 of E1 of that database. And I have generated the next time, let's say a query 1 comes and this is generated with error 2. Now, when I send it with an encrypted match value, that encrypted match value will be generated from this error 1 and error 2. And homomorphic addition, it is directly error 1 plus error 2. And that's why we can send it so that we get the match.